Thank you. Thank you for the kind introduction. Welcome, everybody. It's great to be here at Devoxx Greece. And for me personally, it's fantastic to be back. I was here for the first time in Greece when I was 3 years old in holiday. And it was really an adventure to come to Greece, 3 days driving time. So this is why I can remember this trip. Awesome. So this talk is all about in-memory computing, the big picture. Thanks for joining. And in-memory computing is so in-memory computing is almost everywhere. So this talk focuses a little bit on data processing. So data processing in memory. So important for all modern mission-critical enterprise applications is, of course, high performance. So if I ask the audience who wants the best possible performance, mostly everybody raises hand. Of course, all applications are performance critical. Who is interested in low data storage cost? Yeah, of course, most people are interested in low storage costs. What about license fees, database licenses? Of course, we want to save license fees. That's clear. Low complexity at Java conferences, of course, we talk constantly about clean code, plain Java, not too much dependencies, please. Super important. High security, this is all important for all of our applications. Please interrupt me if something is wrong. In practice, it looks a little bit different. So here I have a cool movie, shows modern use cases for IoT, machine learning, or AI stuff. And all of these applications, of course, need best possible performance. And of course, we want simplicity to speed up our development processes and to make it as simple as possible, because time to market is very important for managers. With our programming languages, and of course we are at the Java conference, so with Java everything is possible. So Java is super fast. I have a lot of discussions with managers all the time. Is Java really fast enough for our use cases? Yeah, of course, for us this is obvious to use Java, but really managers often ask the questions if Java is really a great fit for their use cases. With our JIT compiler, we can execute applications very fast in memory. So we have response time in microseconds or even nanoseconds when we talk about execution something in memory. So everything is possible, which means in Java we can deal with all data types, right? So documents, complex graphs, or now with vectors. So everything is possible with Java. So and because we can deal with any data structure, we can realize every use case, every possible use case we can realize with Java. So the problem is today for data processing, we still use technologies invented in the 1960s or 1970s, and I talk about the database server concept. And who of you uses relational databases, by the way? Okay, so most of you. So of course we are used to use relational databases because they are a de facto standard for decades. The truth of traditional databases is we have a response time or a query time in milliseconds. So what does it mean? So we compare a process time in Java, we talk about microseconds, we compare it with database response time in milliseconds. Milliseconds versus microseconds. This is 1000x faster with Java. Databases are built to deal with a specific data type. So if you use a relational database, you have tables and columns. If you have a graph database, you have a graph. If you have a time series database, you have different data structure. So each database, or every database, has its specific database-specific data structure. And this is the reason why they are built for a specific use case. So maybe this can be a problem. So, and I built this talk because I was very confused about this phrase in memory computing. What does it actually mean, and how can we use it to speed up our database applications? So my name is Markus. I work for MicroStream, which is a startup company. We contribute to 3 Eclipse open source projects. So we are very active in the Java community. We contribute to Project Helidon, which is a microservice framework. We are part of Micronaut Foundation and contribute to Micronaut. And we contribute to the Eclipse serializer project, Eclipse Store project. And this is about my technical background. And we 10 years or 15 years ago, we worked on a development environment. So we built our own development environment for Java. We migrated everything to Eclipse, and then we worked for more than 10 years on improving the Hibernate tools for Eclipse, and tried to make it more simple and faster. All right. So why in-memory computing? In comparison with access to a hard disk drive, in-memory computing is extremely fast. It's everywhere, but we talk about today about executing stuff in DRAM. So I mentioned already, Java as a programming language is extremely fast. So I grew up with assembly programming, and even with the old computers, we had access time in microseconds. So everything executed in memory is fast. The question now is, where are the latencies? Let's have a look on the architecture. So I like to dive a little bit into more deep to show where the latencies are. So traditional database server concept. We have a JVM, we have a Java program in the relational database, and when we have a look inside the database, most people is clear what's inside the database, but it's important for the next steps of our talk to have a look inside this black box, because mostly we just send the SQL to our database and then okay, everything is executed by the database. It's not interesting for us what's going on inside the database. So we have, of course, a lot of memory, obviously, because a database server is a big monolith. So the more memory we have, the faster it is, because internally database also uses caching in memory computing to speed up the whole database process. Then we have, of course, a database management system, cares for concurrency, locking, and so on. And then we have also, depends, we have maybe business logic inside the database. Who of you uses store procedures or store functions or something like that? PLSQL programming? Okay, some. Because in Java, actually, we don't need it because we say, we don't like procedures and functions. We have Java. It's even better. So actually, we don't need this database stuff. We implement business logic in Java. And of course, we have storage and we have a server, obviously. This is very important for later. And in the cloud, sometimes the storage maybe is also running remote on a storage server. So we have maybe wire in between the database server and the storage server. It's also important because wire between the application and the database server means here are latencies. and we talk about millisecond latencies when we communicate via wire. So this slows down our application. So this is inside a database. And when we implement an application using maybe JPA, Hibernate, who of you uses Hibernate, by the way? Okay. So what's the problem actually with Hibernate? So in Java, everything is object-oriented. Of course, we can deal with any types. We can build our object model freely. As soon as we want to store data, everything is different, because now databases introduce a relational model. It's completely, from a technical perspective, incompatible with the Java object model. So you cannot store your Java objects seamlessly in a relational database, obviously. So we have some mismatches here, and this is part of the problem. Now the challenges begin. So we have impedance mismatches, and we have to solve this problem to be able to store objects in a database. So the interesting thing is, what about the modern NoSQL databases? Are they better? What is your opinion? Who uses NoSQL databases? Okay. So maybe it's hard to answer if they are better or not better than relational databases. The cool answer is they are different. What is different? They introduce completely new data model or a data structure, like key value stores, document store, graphs, or now vectors. So why actually? Maybe there are use cases and challenges with relational databases, so we wanted to invent something new, to do it differently. So this means you can store data in a different way. You don't have to use relational databases for any purpose. Interesting. So different data structure for different use cases. You can read of this impedance mismatches in the internet, so you'll find a lot of articles about it. Obviously, the problem is solved because we have a lot of database applications in Java. So what we have to do is we add an object relational mapping framework that cares for storing our objects, because the initial idea is I want to store objects. And this is why in the 1990s they invented the object-oriented databases. So this was when the object-oriented programming languages came up. It was obvious that we invent an object-oriented database because we want to store objects. But something obviously went wrong because they didn't want. So the relational databases are still standard. So what we did, we add a layer to enable us storing objects. But in reality, of course, the framework will create SQL and store the data inside a relational database. What's the problem with object relational mapping? There are a lot of challenges. The data types, the data model, and so on, and of course, performance. Who of you has some performance issues with Hibernate? Okay, someone, yeah. So we all have performance issues. When we built this development environment for Java, all of our users had performance issues with Hibernate. They were contacting us, why is this stuff so slow? They came from other, maybe PLSQL programming, and their SQLs were executed so fast. Now I migrate to Java and everything is so slow. Why the hell? I mean, we will show a performance demo later and it shows why it's so slow. But this is also solved because now we can add, of course, a cache. So now let's add a cache here. So now the result sets are stored in memory, and this is great because so when we want to execute a SQL, then if the same query was executed already, then we can read data directly from cache, and actually it should be executed in microseconds, right? No, mostly no. When we did our performance tests with this development environment, we were surprised because why is it so slow? So when we fetch data directly from a JPA cache, then we talk mostly about milliseconds. But actually, you should have a microsecond response time when you read data from a cache, right? So the problem is that the cache serializes data into the cache, and when you read data from cache, you have to deserialize data. And this takes milliseconds in any case. So it almost doubles your query time. That's crazy. So you can accelerate by using a local cache your application, but maybe you will not get microsecond response time. So we have many different JPA cache provider like Redis, Hazelcast. They are famous. Cache, Oracle Coherence Memcache is very popular, and I think this is very common stuff. So what about a distributed cache? Who of you uses distributed cache, like Redis? Okay, interesting. So when we build distributed systems, then we have more challenges, because if data changes in one of our JVM node, one of our instance, or our cluster node, then and we store data, then this node and the database are in sync. The problem is all the other nodes are not in sync with the database. So we have a problem with consistency here. So, of course, this problem is solved because now we have to change our cache strategy. We just put the cache in between our application and our database. Of course, in the cloud, we want to avoid a single point of failure, and this is the reason why we run a distributed cache. So, and this confused me for the first time because we talk about in-memory computing, but if your application wants to get access to the data, it's not really in memory. It is in memory, but it's in a cache server that runs remotely, and it's connected via wire. So you have wire in between. So you cannot expect that now you can read data from a distributed cache and you have a microsecond access time. Impossible. So, and if the load increases on your database, of course, you will use a database cluster, maybe also for high availability or other purposes. And we can see our architecture grows more and more. It gets more and more complex, more and more nodes, which means more and more machines running. And keep in mind, the DevOps will tell you, please save memory, right? Because memory is expensive. Okay. And please use, it's very important, stateless services, stateless, please, and small memory sizes. Reality is, we do this on the application layer, and we are very careful, but in a caching layer or in a data storage layer, we don't care because maybe there is another team responsible for that stuff. So, and here we have obviously big machines, we have monolithic database applications running, and we need a lot of memory. Distributed caches. And here we can find the same vendors, Redis, very popular, Hazelcast, of course. Okay. So what about in-memory data grids? Who of you uses in-memory data grid? No one? Okay. Sometimes, maybe. So the question is, what the hell is in-memory data grid? So, the vendors, they expanded their solution with capabilities for distributed SQLs, for distributed computing, and this is very specific stuff for specific use cases. But the functional principle is very similar to a distributed cache. So infrastructure is pretty much the same, but it's extended with distributed SQL capabilities or distributed computing for specific use cases. And here we can find almost the same vendors. So most of the vendors, when the in-memory data grids became popular, they implemented more and more features, and so now they are the same. We can see we have the same vendors here on the landscape. Database specialists, they are very they're very focused, of course, on their database, and they are very convinced that their database is the best software, best thing in the universe. But the question is, what about searching servers? Who of you uses Elasticsearch? Why? Why do you use Elasticsearch? Database is fast enough. So when we use a distributed cache, it's cool because we can store data in memory, but we just fetch result sets from memory, and maybe it would be cool when we can now use searching or filtering on this in-memory data. And this maybe is the reason why searching servers became very popular, because in many cases the database is maybe not fast enough, because when we have these complex joins, then your queries become very slow. So maybe a searching server is more is faster than your database. So great idea. Let's add a search server. This is not a problem. This is common stuff. But you can see our architecture grows more and more products, more and more machines are required. Here we can see some vendors, of course. Elasticsearch, this is here the de facto standard in terms of search servers, but you also can find a lot of like Solar open source products. And can check this out if this meets your requirements for your applications. And then we have again the in-memory databases. So another category. What's the difference between a distributed cache, in-memory data grid, and in-memory database? So with the in-memory database architecture, we add an in-memory database to our application. We run it within, maybe if you use a Java memory database, run it within your JVM, within your application process. Then we talk about an embedded in-memory database. The database management system runs in memory, and mostly the whole database also is kept in memory. This is not mandatory in any case, but mostly it's the case that then we load the whole database in memory to speed up query time and searching time. What about distributed applications? If we have an in-memory database in all of our application instances, we have the same problem with consistency. This is not a great approach. So we should better put the in-memory database between the application and the storage. And here we can see we not only have an in-memory database, because we also need storage. So we have our traditional database also in use, which means we need more machines. And here we have the same. We talk about in-memory databases, we talk about in-memory stuff, but there is wiring between your application and your in-memory database. The advantage, of course, is you have full SQL support. You have, if it is a relational in-memory database, of course. So, it depends on your use case. It depends on the knowledge of your teams, which solution is best suited for you. Here we can see some vendors, popular vendors like SAP HANA, Oracle, of course, and also Redis. We can see Redis. Redis says we have a database. A lot of developers, they know Redis as a distributed cache. So this is what confused me in the past. So yeah, what actually is now Redis? Is it better for using as a cache, or is it a database? So, and it really depends on your use case. You can use most of these products in different ways, but you should check this out and choose whatever fits best for your use case. So with microservices, now we have another challenges to solve, because with microservices we have new kind of rules for system architecture, system design. Now we split the monolithic application into numerous of services. They run in their own container, on a container platform. That's great, and every microservice should be small and tiny and should be responsible for a specific use case. And there's another interesting rule. Each microservice that deals with data should have its own database. This might be challenging. And in a big application, in a big enterprise application where you deal with different use cases, maybe you have the need for different database systems because of you deal with complex data, you use a graph database, you deal with sensor data, maybe you use a time series database. So a lot of multiple databases and a lot of multiple database systems for different data types. And there are a lot of many other challenges with microservices and databases. Why actually? Maybe it's obvious because with microservice, it's a completely different paradigm. So because we want to avoid using a monolith. But what is a database server? It's a monolith. So, and then here is our final landscape. We not only have a distributed monolith, we have now multiple microservices, and each microservice should be scalable, horizontally scalable, which means each microservice is a kind of cluster. So you have then multiple clusters running, you have a lot of machines. The applications or the microservices, of course, should be stateless, very important. But when we have a look into the layers below, then there are stateful machines, big machines, a lot of memory. And if your managers are asking, why are our cloud costs skyrocketing? Please take a picture and send it to your manager. This is maybe one of the reasons. Actually crazy, but this is common stuff. So in Eclipse Foundation, we are working on a new project because when we worked on the development environment 10 years ago, we were thinking about couldn't we make this better? And then we found a great solution. So we are not genius, but the cool thing is we've really found a great solution, and it's Java. We already have a great solution. And now I'd like to show you how fast Java is in comparison with all of this database stuff, traditional database stuff. And the question is it suited for your use case? You decide, and let's have a look how this works. So we now talk about in-memory data processing with pure Java. Why? So I mentioned it already. Java is very fast. Everything that's executed in memory is extremely fast. So I remember a talk, Brian Goetz talked, he said with the JIT compiler, it's so highly optimized that we really can outperform C applications in some cases, maybe. That's great. Most managers think C is the fastest stuff, but we are faster than C. Wow, great. And what about data structure? We have the best data structure, better than all these databases. We have Java object graphs. What does it mean? So we have Java objects, we can deal with any data structure, we can deal with documents, we can build a complex graph, all objects are connected. Yeah, we can deal with vectors, everything is possible. So this is this is a multi-model data structure, and the database vendors, they are very hardly working on a multi-model approach, and we have it in Java from the beginning. We have object graphs, and we also have a fantastic query language. We have Java Streams API. You can search and filter in microseconds. So even if you have gigabytes, or even if you have terabyte data in memory, and you search with Java Streams, it will be executed in microseconds. It's amazing. And now I like to show you a performance demo, because otherwise nobody believes me. And even Java developers have concerns. So here we have a bookstore demo. The code is on GitHub. It's a very simple demo. We have around 250 gigabyte data. Actually, we have built two applications that run in parallel. So one is running with the traditional JPA stack. We use Hibernate, cache, and a PostgreSQL database, and this is the yellow bar. We use Spring Data. You can see the query code, and the other application is built with pure Java. It's just a JVM. We execute everything in memory using core Java stuff, no fancy invented by us. It's core Java stuff, just Java Streams API. You can see every single query is executed at least 10x faster, sometimes more than 1,500 times faster than the comparable JPA query. No applause. Okay. Yeah, thank you. Thanks to Java. Yeah, thanks to... Yeah. Fantastic. So, who of you uses in-memory computing with Java just by using Java Object Graphs, Java Streams API instead of a database? Okay. 3 people only. Why? Okay. Let's add some Streams API talks here. Okay, what's the problem actually? Yeah, so there is a problem. There was a problem in the past. It's because of the only thing missing in Java. This is the problem here. We cannot store data. We cannot store data in Java, unfortunately. So if our machine will crash, we lose data. By the way, there is an architecture approach. It's called system prevalence. And this says, so we keep data in memory and we use the features of our programming language. And to get persistence, we just store the objects on disk. Use any technology for that. This is system prevalence. And in terms of storage, there is also an interesting invention, and all of you use it already. In comparison to databases, cloud object storage is extremely cheap. This is an example on AWS. It's a PostgreSQL as a service, just a small database server, 4 CPUs, 16 gigabyte memory. Costs around $8,000, depending on which region. So you can choose different approaches, but around $8,000 per year. And if you run multiple nodes because you want to have high availability or so load balancing for higher loads, then your price, of course, will double or triple. And for 6 nodes, you would pay $50,000 per year. If you use a cloud object storage like AWS S3, 250 gigabyte costs you only $70 a year. And you have data center replication, high availability, everything is included in just $70. Okay, we have to add some more cost for traffic, but 70 to 8,000 is really amazing. So now the question was, can we now connect the performance of Java with the low storage costs of the cloud providers? And by the way, of course, all the other cloud providers, they offer pretty much the same solution, object storage. So with the Eclipse project, Eclipse Store, we can now add persistence to the JVM. This was the idea of this project. And it's completely open source. It's an Eclipse project. Who of you knows Eclipse Foundation? Okay, most people think or know Eclipse from the Eclipse IDE, but the Eclipse Foundation, of course, provides a lot more. 100 open source projects. For example, all the specifications like Jakarta E are defined in the Eclipse Foundation process, microprofile, and also great JVM, the OpenJ9. And with Eclipse Store, we get now persistence for Java objects. And this is, in my perspective, a Java developer's dream come true, because core Java stuff, no database, fancy stuff, you can deal with all Java types, and you can just store your objects, and you can restore it at any time when needed. You can benefit from 1000x faster in-memory data processing with Java. It's super easy to use because it's a small, tiny library. You just add via Maven, and you can now store your objects persistently on disk without the need for object relational mapping or any mapping or data conversion. There is also no conversion like JSON serialization, so nothing. You just store it by using serialization. The clue here is that we don't use the Java serialization because of a lot of drawbacks of the Java serialization. So how does it work? So back to our architecture overview, we replace the object relational layer with Eclipse Store as a persistence layer. So because we keep data in memory, because our object graph now becomes our in-memory database. So we keep data in memory, which means we don't need a cache anymore. So we also can skip our cache layer. So when we have a look inside the database, what do we need from a database? Actually, nothing. The only thing we need is storage. And we create a binary representation of our objects in memory and store the binary persistently on disk. The cool thing is we can not only store the binaries in plain files, we can also store it in an object store like S3, and we can, this might be confusing, but we also can use a traditional database to store the binaries because they can store binaries. So we support various storage targets and also the traditional databases. But keep in mind, there is no more mapping to the database-specific model. If you use MySQL or PostgreSQL for storing the binaries, you don't get the relational model. There's no relational mapping anymore. This library runs wherever Java runs. This requires Java 11 Here's here we have Java 8. This is now running with Java 11 or newer. And very important, we don't have to load the whole data into memory. So it works with lazy loading, which means you can have a 250 gigabyte database or a data storage, and you only have, let's say, 2 gigabyte memory. This concept will work. So because we load only data memory we really need, and it's access to data is super easy because you just have to call a get method, and the engine will load the object reference dynamically from disk and merges your object reference directly in your object graph. So no more classic selects, no more merging, dealing with object copies or something like that. So everything is managed by the framework behind the scenes. Eclipse Store itself is built to run in a single JVM. And we also provide a distributed solution. This is pretty new. Today, it's called Microstream Memory Data Platform because we built it as a commercial product. Actually, I wanted to announce at the other developer conference that we open source it, but it's so new now. Oh, it's recorded, so I can't get back now. So we announced that we open source Microstream cluster and becomes Eclipse Store cluster, and so the whole stack will be open source for you guys. And so now you can build even distributed applications by using Eclipse Store, and you can distribute your object graph through multiple hundreds or even 1,000 JVMs and distribute your load, and you can use it for distributed monolith as well as for microservices. And then you can replace most of your data solutions if you like the approach. So this is very important. The only thing is we need an Eclipse Store cluster. We can replace a search server. We can replace a distributed cache. And the cool thing is we can also, you can keep your traditional database, run it as a primary database. But if you have trust in the solution, you can also use Eclipse Store cluster as a primary data storage, and then you save a lot of machines. And the only thing you use is core Java stuff. So a flat learning curve, there is no more database specific stuff to learn. It's just core Java stuff, nothing else. No query language to learn, no Java API for wrapping the query, database specific query language, no mapping stuff, nothing. So we run out of time. So the whole stack is very simple here. It becomes also, it should become a standard. So we're working on a standard for the functional principle. This is not decided already, but this is expected to create a standard within the microprofile working group. Eclipse Store becomes the reference implementation, and the cluster becomes also open source. So if you like to learn more about this, you can download Eclipse Store on the Eclipse Store IO, check it out, and check out if this works for your use cases. So in-memory computing is really huge, and you should definitely use it. Yeah, you can also find free courses, online training courses at Java Pro IO. This technology is not for all. So database guys don't like it. And Java people mostly like it, but it always depends on the use case. So check this out. I hope you enjoyed Devoxx. It was a pleasure for me to be here. If you have any questions, I will be here. I guess we have some minutes for Q&A because I'm less speaker. So for all of you, I hope you enjoyed Devoxx. For me, it was fantastic to be here. Hope to see you next year again. Thanks for coming. Goodbye and have a great time have a great summer in Greece. Thank you.
Thank you so much. If you have any questions, raise your hand so I can give you the microphone. And if this is for you, olive tree.
Thank you. Great.
No, thank you for being the closing of the event.
Hello, thank you. Great presentation. Very, very promising. I didn't know this stuff existed. I have actually 3 questions. I don't know how many we can have time to respond. Actually, in the benchmark testing, you showed us there were 250 gigs of data.
Yep.
How much RAM did you have available for this benchmark testing? Only 2 gigs? Do you remember maybe?
I'm not sure. I think it was just a 4 gigabyte memory machine. Yeah. Because we wanted really to use common stuff. And of course, the more memory you have, the better it is, the faster it is. And it's because of, then you can preload more data in memory. There is no more, or there's lower I/O. And of course, I/O is always slow. It's the same with Eclipse Store. So the more memory you have, the better it is. But it depends on the use case, because of if you need a faster startup time, you cannot preload that much data in memory. If startup time is not an issue for you, then you can preload more data, and then of course, then data is available in memory. Then it will be faster. But it works great with small memory sizes. You can use lazy loading, and this is very important.
Okay. The other question is this accessible by the customer by any means? Could it be accessible by a customer? Could this be externalized?
Sure. Very important question. Normally you get a t-shirt, but I have no booth here. So accessibility, very important. So keep in mind, this is not Eclipse Store specific stuff. We talk about is Java accessible, because everything that is in memory is core Java stuff. So if you run a Java application, how can a third-party application get access to your Java application? That's the question. Yeah, we have a lot of different approaches. You can use REST, you can use GraphQL, and these solutions are supported by third-party applications like reporting tools. So this is the common
so
stuff.
It's up to us to create the integration for this. Okay, and the last one. You shared us all the advantages. What are the disadvantages? I mean, can you describe a scenario where this is not suitable?
No.
Okay.
To be honest with you.
I mean, you said that there are snapshots. So is that so? Could we trust this? How frequent are these snapshots? How easily you can take them? How fast you can restore them?
Another great question. You get another t-shirt with a different size. It creates snapshots, but you as a developer, you define when the snapshot should be created. So we recommend after every single change on your object graph, and it's just a store method. You call a store method, and then a snapshot is created by the changes of your object graph, and it gets serialized to disk. So and when you call a store method, this is a transaction safe all or nothing operation. It's ACID compliant, and it guarantees you that data is really stored, and it's stored appended to your file storage. So each store appends your data to the file storage. We never overwrite data in a storage. So transaction safety. And of course, every solution has drawbacks, so it was a joke. But there is no specific use case. It's because we store objects. When do you use objects? For what purpose? For every purpose. Yeah, so now we want to store objects, so it's not built for a specific industry or for a specific application. type of application, but it's not suited. And it's really not a joke. It's really the truth. It's not suited if your organization is not ready for that. If you have Java developers, and this is really the biggest challenge. Even Java developers very often think relational because we grew up with relational databases. So if I tell you, please create a software for me. I want to store customers, products, and so on. Your brain will create an object, will create a relational model in milliseconds. So, and I must say, stop thinking relational. Think like a Java developer. So you have now to build a Java object model. Forget everything you've ever heard of a relational database. Does not exist. Imagine you only have Java. There is no database existing. What would you do? How would you organize your data? How would you store your data? So you have to think different. And a lot of Java developers are not ready for that. Or you are ready for that, but your organization is not, because you have some DevOps in your team, you have some database admins, and they will tell you you are crazy. How can I get access to your Java stuff, huh? So what about SQL, huh? So this is the biggest problem, biggest challenge we're facing. And so this is the reason why it's not suited for every use case purpose. Maybe it's also not suited if you have an existing application, you have a lot of stored procedures already. So it depends on, do you want to migrate or not? So it's not a drop-in replacement. You cannot just skip JPA, insert, implement Eclipse Store, and it's up and running. It's not the case. Migrating is not complicated, but you have to do, there is a migration path, but you have to do changes, because you will build a different data model. You will build an object model.
Okay, thank you very, very much.
Thank you.
I'll email you my address for the t-shirts.
Yeah, I come back next year with a booth and with t-shirts.
So where this data in memory lives, outside VM, outside heap, or inside?
Again, a great question. Everything is managed by the JVM. It was very important for us that we don't build something around the JVM. So JVM is the boss, so when we preload data, then we will store the objects directly in memory. But at this point, JVM takes control of your memory management. Everything is on heap. There is an exception. We provide an indexing concept, and this indexing is managed off heap. But this is a different story.
Yeah, but the whole data actually are garbage collected eligible, let's say. So it seems that in your tenure, you have a big thing, a big stuff there, stays there, right? Because it's inside the heap.
Yeah, but you have full control of...
So can I move this data outside of the heap so the garbage collector does not care about that?
The garbage collector will always care about it. So this is what we wanted, and you have control of your lazy references. So you can remove your lazy references from the memory by just calling a method. You can define a timeout, and so you can influence your memory, of course. But garbage collection is done by the JVM. It's only done if the object is not reachable anymore.
Yeah, what I mean is that I have a tenure, I have a space, a memory part, that actually some of that is log living, right? I have my data there. So I need to scale up somehow my VM in order for the whole application to go and, operate better. Because I'm located some memory there which stays there, and it's only for this storage, right?
Okay.
What I mean is that maybe I need to tune up a little bit the heap memory so I can still have my application working and garbage collector is also working perfectly better.
I'm not sure if I get it right, but it's separated from your application stuff. So Eclipse Store, you need a root object. So you create an Eclipse Store instance, and then you have a root object. And it's comparable to a Java Swing tree. I don't know who of you has developed in Swing already. So you have and then all objects that are reachable from this root objects can be stored. And this is the only thing we touch. All the other stuff in memory we never touch. It's fully controlled by your application or by the garbage collector. Maybe we can talk later if I don't get it right.
Anyone?
I would like to know how this concept works with distributed computing. If you have two services working on the same data, updating them, and so on.
Yeah, great question. So for this scenario, you need the cluster solution, and it enables you to start multiple instances of your application or your service. And the cluster solution provides you replication, and each store is then replicated through all JVMs and will update your object graph through the whole cluster solution. The cluster is a single writer approach. It's eventual consistency from as a standard model, and this is required for building distributed systems.
Hello, very nice presentation.
Thank you.
I wanted to ask, are all the use cases, assuming that the application itself is there, I mean with the business logic and everything, including the store, or do you see, are there any use cases where the store could be a separate, let's say, cluster where your applications talk to, just which handles only the storage? Would that be a use case?
I don't know if you get it right. Can you please repeat your question?
So you have your application which has the store in it, and then you have a cluster, let's say,
Yep.
2 replicas or 3 replicas. So this is the main use case, right? Your business logic is running in the same application where your store is and the storage is happening. Is there any use case where the store part would be a separate cluster?
Yeah.
Your applications would be integrating with it?
Yeah, that's also great because there are really different possible architecture approaches. So I showed the approach where the storage engine runs within your business logic, and if you have a cluster, then the cluster runs your business logic and storage. This is the fastest approach, and it's because of, yeah, it's clear, but you also can separate it. You can run your business logic as, let's say, stateless microservices, and accessing an Eclipse Store cluster where only the queries are executed. So then it works like a classic database cluster, let's say. You can access via REST, for instance, and this is the use case is, yes, when you use lambdas, for instance, so stateless microservices. If this is important for you, then this is the way to go. And it's also an organization topic. So if you can really decide where you run, which layer do you want to run, then it might be not an issue. But maybe you have a DevOps team and they will tell you everything that's related to storage we have to run on this and that infrastructure. So please implement your business logic in this layer and run MicroStream in this storage layer. This might be a reason. This is absolutely possible. And the cool thing is, imagine you have a data storage layer like a cache, but there is no database specific logic to execute, no database specific query language or database language like PL/SQL. It's core Java stuff. You can implement everything you like. It's pure Java stuff. That's fantastic. And it runs with any JVM. And the cool thing is, it also depends on what JVM you use. The latest Java versions are the fastest we measured. So that's fantastic. So, and even there are differences between the JVMs itself. OpenG9 is great, for instance. And so you build an application, provide it to your customer, and 3 years later or 4 years later, you have a new Java version. It's 20% faster. You can provide a great update, charge your customer and say, wow, we accelerated your application and you just made a Java update. Great. You benefit from Java. Any further questions? Yeah.
And so the classic problem with serialization is some object is changing, let's say activity takes name.
Yeah, great question. So we worked more than 5 years on implementing a new serialization, and it's because of it can deal with complex object graph structure. It's highly secure in comparison to Java serialization. It's way faster, and it's now launched as Eclipse Serializer. By the way, if your class is changed, it was really a big challenge. And this is the reason why this concept is not used so far, because a lot of developers told us we had the same idea 15 years ago, yeah, using just serialization for storing objects. If your classes change, you're in trouble. So we added a concept, it's called legacy type mapping. And it's very simple, and imagine the object is loaded, the object reference is loaded in memory, and then the engine will compare your object with your class. If there are changes, then the engine can solve simple cases automatically. Simple cases, if you add a field, remove a field, rename a field, change a primitive type, this can be handled by the engine automatically. You store your object, then you have a new object in the storage. The old object version and the new object version. And as a developer, you can define whether you want to keep both versions in a storage or let the Eclipse garbage collector, it's a garbage collector for the file base, let the garbage collector remove the older objects from your storage. For more complex cases, you can define a legacy type mapping if you add an object or something like that. That's solved. Thank you, thank you. And by the way, this is not experimental. This is not experimental. Companies like Allianz, Fraport in Germany use it already. Arabic hospital, we have a huge project there. More and more companies use it in production already. So check it out. If you have questions, reach out. And thanks again for joining. It was awesome to join talk with you. See you next year. Thanks.